Hello, my dear students. Welcome to ESR chemistry classes. Here we are in lecture number 11 on ESR spectroscopy applied to inorganic chemistry. In this video, we are going to discuss Kramer degeneracy. We have already seen that if a species contains more than one unpaired electron, the spin degeneracy can be resolved by the crystal field also. It means if a molecule or ion contains more than one unpaired electron, the spin degeneracy can be lifted, can be removed, can be resolved by the crystal field also, that is, by the magnetic field produced by unpaired electrons. The splitting of spin energy levels in the absence of magnetic field is called zero field splitting, which has been discussed in detail in the previous video. However, if the species contains an odd number of unpaired electrons, the spin degeneracy of every level except ms equals to 0 remains doubly degenerate. Let us see it again. If the molecule or ion contains odd number of unpaired electrons, the spin degeneracy of every spin energy level except ms equals to 0 remains doubly degenerate. This is known as Kramer degeneracy. On the other hand, if the species contains even number of unpaired electrons, the spin degeneracy may be removed completely by the crystal field. It is obvious from the above discussion that the Kramer degeneracy is observed in the case when the molecule or ion contains odd number of unpaired electrons. On the other hand, if the number of unpaired electrons in the molecule or ion is even, such as 2, 4, 6, etc., the spin degeneracy of all the spin energy levels may be removed completely by the crystal field. Let us illustrate it taking example of Mn2 plus ion. The atomic number of manganese is 25. Its valence shell electronic configuration is 3d5 4s2, and accordingly the valence electronic configuration of Mn2 plus ion will be 3d5. Its box diagram is shown here. This is 3D subshell containing 5 electrons, and these 5 electrons fill up in the D subshell one by one in accordance with Hund's rule, and thus there are 5 unpaired electrons in Mn2 plus ion. Mn2 plus ion contains odd number of unpaired electrons. The number of unpaired electrons in Mn2 plus ion is 5. This is resultant spin angular momentum quantum number capital S, which is equal to summation of ms values. In the case of Mn2 plus ion, all the 5 unpaired electrons have ms equals to plus 1 by 2. And on adding plus 1 by 2 values 5 times, the value of capital S is 5 by 2, and the spin multiplicity 2s plus 1 will be 6. If we put s equals to 5 by 2 in this expression, we get 2s plus 1 equals to 6. The value of L, resultant orbital angular momentum quantum number, is equal to summation of ml values of all the electrons. The first electron has ml value plus 2, the second has plus 1, the third has 0, fourth has minus 1, and the fifth unpaired electron has minus 2 ml value. And on adding all these ml values, the value of capital L is 0, and the spectroscopic state is called S. The value of J varies from L plus S to L minus S in integral steps. Since L is equal to 0, the value of J will be 5 by 2. The ground state term symbol for Mn2 plus ion will be sextet S 5 by 2, which can be written simply as sextet S. The zero field splitting produces 3 doubly degenerate spin states for Mn2 plus ion, and these are plus minus 5 by 2, plus minus 3 by 2, and plus minus 1 by 2. These three spin states are doubly degenerate, each having two spin energy levels having the same energy. When an external magnetic field is applied, each of these doubly degenerate spin states are split up into two singlet spin states, producing total 6 spin energy levels, and these are plus 5 by 2, plus 3 by 2, plus 1 by 2, minus 1 by 2, minus 3 by 2, and minus 5 by 2. In the case of Mn2 plus ion, the zero field splitting produces 3 doubly degenerate spin energy levels. But on applying external magnetic field, each of these doubly degenerate spin states are split up into two singlet spin states, producing overall 6 spin energy levels. As a result of this splitting, 5 transitions among these 6 spin energy levels are allowed as per the selection rule. Delta ms equals to plus minus 1. According to this selection rule, 5 transitions are allowed among these 6 spin energy levels as shown below. ms equals to minus 5 by 2 to ms equals to minus 3 by 2. ms equals to minus 3 by 2 to ms equals to minus 1 by 2. ms equals to minus 1 by 2 to ms equals to plus 1 by 2. ms equals to plus 1 by 2 to ms equals to plus 3 by 2, and finally ms equals to plus 3 by 2 to ms equals to plus 5 by 2. Please note that all these 5 transitions between spin energy levels involve delta ms equals to plus 1. Complication in ESR spectrum of Mn2 plus ion. Nuclear spin, that is I, for Mn2 plus ion is 5 by 2. The ESR spectrum of Mn2 plus ion is further complicated by the hyperfine splitting. Number of hyperfine lines is equal to 2ni plus 1. Here the value of I is 5 by 2, while the number of Mn2 plus ions is 1, and accordingly on solving it we get 6. Each of the 5 peaks in the ESR spectrum further split up into 6 hyperfine components as a result of nucleus electron coupling or hyperfine interaction. In the ESR spectrum of Mn2 plus ion, 5 peaks are obtained due to allowed transitions between 6 spin energy levels, and each of these 5 peaks in the ESR spectrum further split up into 6 hyperfine components as a result of nucleus electron coupling or hyperfine interaction. It has been demonstrated by diagram here. Sextet S is the ground state term symbol for Mn2 plus ion. Its capital S value is 5 by 2. Due to zero field splitting, that is a splitting caused by crystal field, this S equals to 5 by 2 energy level splits up into 3 doubly degenerate spin energy levels plus minus 1 by 2 plus minus 3 by 2 and plus minus 5 by 2. And when external magnetic field is applied, Ms equals to plus minus 1 by 2 a spin state splits up into 2 singly degenerate spin energy levels, Ms equals to minus 1 by 2 and Ms equals to plus 1 by 2. Similarly, Ms equals to plus minus 3 by 2 energy level also splits up into 2 singly degenerate spin energy levels, minus 3 by 2 and plus 3 by 2, and likewise Ms equals to plus minus 5 by 2 spin energy level, which is doubly degenerate, also splits up into 2 singly degenerate spin energy levels, Ms equals to minus 5 by 2 and Ms equals to plus 5 by 2. This splitting is caused by applied magnetic field, while this splitting is caused by crystal field effects, that is magnetic field produced by unpaired electrons, and due to interaction of nucleus of Mn2 plus ion having I equals to 5 by 2. Each of these spin energy levels are split up into 6 sub-energy levels due to electron nucleus coupling, due to coupling between unpaired electron of Mn2 plus ion and its nucleus. These 5 transitions between spin energy levels are allowed in accordance with the selection rule delta Ms equals to plus minus 1. These transitions take place from Ms equals to minus 5 by 2 to Ms equals to minus 3 by 2. This take place between minus 3 by 2 and minus 1 by 2. This transition takes place from minus 1 by 2 to plus 1 by 2. This transition takes place from plus 1 by 2 to plus 3 by 2, and finally the fifth transition takes place from plus 3 by 2 to plus 5 by 2. And each of these 5 peaks in the ESR spectrum of Mn2 plus ion are split up into 6 hyperfine lines due to interaction between the nucleus of Mn2 plus ion having I equals to 5 by 2 and the unpaired electron. In some cases, the zero field splitting may be greater than the energies of ESR transition. The zero field splitting may have greater value than the energy required for ESR transition. In certain cases, zero field splitting exceeds the energies of usual ESR transitions. When it happens, it is not possible to observe ESR transitions involving delta ms equals to plus minus 1. However, it has been possible to observe a weak transition involving delta ms equals to plus minus 2 as exemplified below. Let us see it again. In certain cases, the zero field splitting is greater than the energy required for usual ESR transition, and in such cases, the transitions involving delta ms equals to plus minus 1 are not observed. However, it has been possible to observe a weak transition involving delta ms equals to plus minus 2, such as ms equals to minus 1 to ms equals to plus 1. This transition involves delta ms equals to plus 2. Let us illustrate it taking example of vanadium triple plus ion. The atomic number of vanadium is 23. Accordingly, its valence shell electronic configuration is 3d3 4s2, and therefore the electronic configuration of vanadium triple plus ion will be 3d2 after the electronic configuration of argon. The box diagram for vanadium triple plus ion is represented here. Here, two unpaired electrons are present in 3D subcell. These are ml values of various boxes plus 2, plus 1, 0, minus 1 and minus 2. These are the ml values of various orbitals of the D subcell. Resultant spin angular momentum quantum number will be equal to summation of ms values plus half and plus half. These will become plus 1, and 2s plus 1 will be equal to 3. If we put the value of s equal to 1, the spin multiplicity will be 3. Capital L, that is resultant orbital angular momentum quantum number, is equal to summation of ml values. The first electron has ml value plus 2 and the second electron has ml value plus 1. On adding, we get capital L is equal to 3, and this is F state. And 2s plus 1 is triplet state. Capital J varies from L plus S to L minus S. L plus S will be equal to 4, the highest value, and the minimum value L minus S, that is 2. The value of J varies from L plus S to L minus S in integral steps, and accordingly there are 3 values of J, 4, 3 and 2. Since the subcell is less than half filled, the minimum value of J will be selected for the ground state, and accordingly the ground state term symbol for vanadium triple plus ion will be triplet F2. It can be written simply as triplet F. The zero field splitting of vanadium triple plus ion produces one doubly degenerate spin states, ms equals to plus minus 1, and a singlet spin state, ms equals to 0. The zero field splitting in the case of crystal of vanadium triple plus ion produces one doubly degenerate, ms equals to plus minus 1, and one singly degenerate spin state, ms equals to 0. When an external magnetic field is applied, the doubly degenerate spin state, that is ms equals to plus minus 1, splits up into two singlet spin states, ms equals to plus 1 and ms equals to minus 1, while the singlet spin state ms equals to 0 remains unaffected. Thus, total 3 spin energy levels ms equals to plus 1, 0 and minus 1 are obtained. Two expected transitions. As a result of this splitting, two transitions among these 3 spin energy levels are allowed as per the selection rule delta ms equals to plus minus 1, and these transitions are ms equals to minus 1 to ms equals to 0 and ms equals to 0 to ms equals to plus 1, and both these transitions involve delta ms equals to plus 1. Minus 1 to 0, delta ms will be plus 1. ms equals to 0 to ms equals to plus 1, it again involves delta ms equals to plus 1. But these transitions are not observed because the zero field splitting is greater than energy required for usual ESR transition. The actual situation is as follows. Instead of two peaks in the ESR spectrum, a weak transition ms equals to minus 1 to ms equals to plus 1 is observed, which involves delta ms is equal to plus 2. The nuclear spin for vanadium triple plus ion is 7/2. The ESR spectrum of vanadium triple plus ion is further complicated by the hyperfine splitting. The number of hyperfine lines is equal to 2Ni plus 1. 2. The number of vanadium triple plus ions is 1, having I nuclear spin value 7/2. 2 will be cancelled out. It will be 7 plus 1, that is 8. This line in the ESR spectrum of vanadium triple plus ion further splits up into 8 lines, into 8 hyperfine components as a result of nucleus electron coupling or hyperfine interaction. The ESR spectrum of vanadium triple plus ion containing 2 unpaired electrons consists of one peak arising due to transition ms equals to minus 1 to ms equals to plus 1 involving delta ms equals to plus 2, and this peak in the ESR spectrum splits up into 8 hyperfine lines due to coupling of unpaired electron of vanadium triple plus ion with its nucleus, that is nucleus electron coupling or hyperfine interaction. Diagrammatic representation. Triplet F2 is the ground state term symbol for vanadium triple plus ion having capital S value equals to 1. Due to zero field splitting, this spin state capital S equals to 1 of vanadium triple plus ion splits up into two energy levels, two spin energy levels, ms equals to 0 and ms equals to plus minus 1. When external magnetic field is applied, ms equals to 0 energy level remains unaffected, while ms equals to plus minus 1 energy level, which is doubly degenerate, splits up into two singly degenerate spin energy levels, ms equals to minus 1 and ms equals to plus 1. Now, let us see that this energy required for transition between spin energy levels is smaller than the zero field splitting. Zero field splitting has greater value than the energy required for usual ESR transition, and therefore this transition is not observed, which involves delta ms equals to plus 1. Instead, a weak transition involving delta ms equals to plus 2, that is from ms equals to minus 1 to ms equals to plus 1 is observed. And this peak in the ESR spectrum splits up into 8 hyperfine lines due to interaction of unpaired electron of vanadium triple plus ion with its nucleus having nuclear spin I equals to 7 by 2, and this is hyperfine splitting or nucleus electron coupling or interaction. Thank you for watching the video with concentration. Please like and share it, and if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.